In the 13th lecture, we will cover the goodness of fit and the maximum likelihood in linear regression models. From the last lecture, we know the coefficient of determination R² is the most commonly used measure of the goodness of fit of a linear regression model. However, we may not be able to tell if the linear model is appropriate based only on the R² value. A good value of R² may depend on the area of the application. In fact, different research areas may have different amounts of variability that are inherently unexplainable. For example, when we analyze the repeated science experiments, we may expect a R² more than 90% due to low unexplainable variation. On the other hand, in the social research, a R² less than 20% could be enough for a good model, since the unexplainable variation is normally very high. The coefficient of determination is the explained sum of squares divided by the total sum of squares, which is the sum of the explained sum of squares and the residual sum of squares. So, the R² is a measure of explanatory power, and it is inversely related to the unexplainable variation, which is a noise. Some people doubt the usefulness of R² as a measure of the model fit. They say a higher R² does not always mean a better fit. For example, if we add a large noise on a perfectly linear relationship, then the R² could be only 50% or even lower. On the other hand, if we fit a linear model on data from an exponential distribution, we may get an R² of above 80%. A perfect linear relationship doesn't give us a high R². Instead, a nonlinear relationship gives us a better R². Thus, they think R² should not be used as a measure of the model fit. This is a misinterpretation of the model fit. The model error is the sum of the reducible error and the irreducible error. The reducible error is related to the model correctness. The irreducible error is essentially the noise. When we specify a model that perfectly matches the underlying relationship, the reducible error is 0. But we may still have the noise. The noise may decrease the explanatory power of the model dramatically. If the noise is very large, then the underlying relationship could even be insignificant. Thus, sometimes we may not have a good fit, even the reducible error is 0. For example, if we add a large noise on a linear relationship, a R² of 50% tells us the model may explain 50% of the total variation. Since the reducible error is 0, the remaining 50% of the variation is noise. We may not assume high R² values even there is an underlying linear relationship, unless we can control the noise. On the other hand, a relatively high R² does not mean your model is surely correct. In the second case, we fit a linear model on data from an exponential distribution. We may get a R squared above 80% if the noise is small. Thus, we may still have a good model fit, although the model is not totally correct. Some statisticians may use R squared as a sole measure of fit in practice because it is dimensionless and easy for the comparison, but it is not recommended. Let's say we have two linear models, and their R squared values are the same. So R1 squared is equal to R2 squared. Model 1 has a smaller reducible error than Model 2, and Model 2 has a larger noise. We probably prefer Model 1 since the noise is random and does not introduce additional bias. However, in practice, we are unable to separate the two errors because the underlying relationship is unknown. Also, R squared is sensitive to the outliers. Thus, we should not rely on R squared alone. We may also need to analyze the residual plots. The residual plots may tell us if the model is correct. Another common measure of fit is the mean squared error. It is an estimator of the error. When we have many predictors and need to select the best model as the model selection, we might need additional tests and measures such as AIC, BIC, and CP. To understand the additional goodness of fit measures, we need to introduce the likelihood function and the maximum likelihood estimation. In statistics, the likelihood is used instead of the probability for continuous random variables. Since the probability of a specific value of a continuous variable is 0, the likelihood measures the goodness of fit of the statistical model to a sample data. It is formed from the joint probability distribution of the sample as a function of the parameters. In fact, joint density and the likelihood are the same functions. The joint density is a function of the observations as in the frequentist view, where the parameters are fixed and the sample data may vary. The likelihood is a function of the parameters as in the Bayesian view, where the sample data are fixed and the parameters instead may vary. The maximum likelihood estimation is a method of estimating the parameters of a probability distribution by maximizing the likelihood function. Let's check the maximum likelihood estimation for Bernoulli and the normal distributions. For a random sample following Bernoulli distributions, the likelihood is the joint Bernoulli distribution as this, where p is the parameter. Commonly, we may use the log likelihood to simplify the calculations. The log likelihood is the natural log transformation of the likelihood function, which can be simplified as this. The likelihood is maximized when the derivative dLdP is 0. The estimator PMLE is solved as the sample average. Next, we may also find MLE for a random sample following normal distribution with two parameters, mu and sigma. The log likelihood may be simplified as this, and the estimators can be solved similarly on two partial derivative equations. The estimator mu MLE and the sample is the sample average, and the sigma MLE is the square root of total sum of squares divided by n. The estimator is obviously biased, since the unbiased estimator for the variance is the sample variance, which is the total sum of squares divided by n minus 1. Information criteria methods are used extensively in the model selection. They are based on the maximum likelihood estimations. For example, AIC stands for Akaike's information criterion. It is defined as this. Here, K is the number of estimated parameters in the model, and LM is the maximum value of the likelihood function. When the sample size is small, we may use additional correction, such as AICC. BIC is the Bayesian information criteria. BIC has the log of n instead of 2. For the linear regression, we assume the error is normally distributed. Now let's find the maximum likelihood for a random sample of n residuals with the identical normal distributions. We have the likelihood function as this. Here, EI is the residual I, and the standard deviation is sigma. Since the observation is fixed, the likelihood is maximized when the derivative dl d sigma is 0. Thus, the maximum likelihood estimated variance is the residual sum of squares RSS divided by n, as we discussed in the last slide. When sigma is SMLE, we have an estimated maximum value of the likelihood function LM. Thus, AIC is 2k plus n plus log of RSS over n plus a constant term, which is not related to the parameters. In the model selection, we may ignore the constant since it is independent of the model and does not change unless the data changes. For small sample size, n less than 40 times k, then we may use AICC to address the overfitting. AICC is a second-order estimate, and it equals AIC if the sample size n is large enough. If we compare AIC and BIC, we find BIC penalizes more on k, the number of parameters, since log n is larger than 2 if n is greater than 7. Thus, AIC tends to choose models with more parameters, and BIC prefer models with less parameters. Likelihood ratio test may be used to assess the goodness of fit of two models. The likelihood ratio is the ratio of the two maximum likelihoods as this. Here, omega is the null parameter space, and the capital omega is the entire parameter space. The constant C is selected based on the significance level alpha, and it is between 0 and 1. The critical region is lambda less than C, and if the ratio is in the region, then we reject the null hypothesis. For example, we may test if the population mean is some value with a known population variance sigma square. The null hypothesis is theta equal to theta 0. Lambda is the maximum likelihood when the parameter theta is equal to theta 0 divided by the maximum likelihood when the parameter is free. Since we have the maximum likelihood when the parameter is y bar. We have this. We may simplify lambda as this, which should be less than c. Thus, we have this. Since the circled term is the z-score, the likelihood ratio test may be transformed to a two-tailed one-sample t-test if we select C according to this equation. To assess the goodness of fit, we may use the likelihood ratio statistic capital lambda, which is -2 log of the likelihood ratio. We may have the critical region as this. If the statistic falls in this region, then we reject the null hypothesis. When the sample is large, the likelihood ratio statistic approximately follows a chi-square distribution, with the degree of freedom is the dimension difference between the entire parameter space and the null parameter space. This limiting distribution is called the asymptotic distribution. Let's use the likelihood ratio test on the height example in lecture 8. The likelihood ratio statistic is this, which is 3.24. Since the dimension difference is 1, the statistic approximately follows a chi-square distribution with 1 degree of freedom. At a 5% significance level, the critical value is 3.84, which is larger than the statistic. Thus, we fail to reject the null hypothesis. In summary, we learned that the coefficient of determination R-squared is the most commonly used measure of the goodness of fit of a linear regression model. It is the explained sum of squares divided by the total sum of squares. Thus, it is a measure of explanatory power. The model error is the sum of the reducible error and the irreducible error. The reducible error is related to the model correctness. The irreducible error is essentially the noise. We do not recommend using R-squared as a sole measure of fit in practice. We may also need the residual plots. In the model selection, we might need additional measures such as AIC, BIC, and Mallow CP. The likelihood measures the goodness of fit of a statistic model to a sample data. It is formed from the joint distribution of the sample as a function of the parameters. The maximum likelihood estimation is a method of estimating the parameters of a probability distribution by maximizing a likelihood function. The likelihood is maximized when the derivative of the likelihood with respect to the parameter is 0. From the derivative equation, we may have the maximum likelihood estimation of the parameter corresponding to the likelihood maximum. Measures such as AIC and BIC are calculated from the maximum value of the likelihood function. BIC has a strong penalty for including additional parameters to the model. The likelihood ratio test may be used to assess the goodness of fit of two models. When the sample is large enough, then the likelihood ratio statistic follows approximate chi-square distribution. Its degree of freedom is the dimension difference between the two models.